All right. So probably we'll start. Thank you, Avinash, for joining. I hope soon the other students also join. So today we will just, discuss, or we'll just go through all the concepts that we gone through in this class, and then if you have any doubts, you can ask me. Or for a change, maybe I can. If you have any doubts, Avinash, you can ask me. Maybe we'll go through that and then maybe we can go forward with the revision. Do you have any doubts? Do you want to ask anything?
Sir, right now, no doubt, sir.
Okay, no problem. Then we will go forward and we will revise it. And by the way, whoever is going to view this in YouTube also, so if you had any doubts in between while you are reviewing it, please write an email. I will be able to answer your queries in email. Okay. So this will be our last session in this course, last interactive session in this course. Nevertheless, I will be available if you have any doubts uh, until your exam, final exam. All right. Then we will get started. So this course is about conduction and convection heat transfer. So that is how this course was also divided. So initially first 5 to 6 weeks were dealing with conduction heat transfer, and then we moved on to convective heat transfer, and final week was basically its application in some practical industrial application, which includes heat exchangers. So heat exchangers you will see everywhere. Uh, Not even just industries, in home appliances too. So that is how the course was structured. So initially we started with conduction. So we will go through in that manner weekly. So the conduction, we initially studied what we call it as a Fourier law of heat conduction, right? So there is something called heat transfer, and there is something called temperature. These are the two things that has been introduced. So heat transfer is nothing but energy. We all know energy. We have already studied that in thermodynamics. Here, the heat is nothing but the energy which is in transit. Okay, so whatever energy in motion is what we call it as, or energy which is getting transported is what we call it as heat transfer. Okay, and we can uh, we can define heat flux for a particular direction, something like this, which is heat 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 transfer rate per unit area. Okay, along that direction is what we call it as heat flux in that direction. So what Fourier did is Fourier did some experiments, and he found out that this heat flux, whatever we calculated based on heat transfer rate and area, this heat flux vector is going to be dependent on two parameters. One is uh, the thermal conductivity K, and the other is temperature gradient. Okay, the so these are the two parameters that this heat flux vector depends on. So that he found out from experiments. So it is not coming from any fundamental law. It's an empirical in nature in that way. So in fact, he just found out that heat flux is a function of temperature gradient, and in order to match them, there needs to be some parameter which came out to be thermal conductivity. Okay, and different materials had different thermal conductivity, and that is how he was able to get a different heat flux for different materials. Okay, and similarly, you can also write this heat flux vector in a 3D, which will be k times gradient of T. Here gradient is an operator, and the temperature is a temperature field which is going to vary with respect to x, y, and z. Okay, so this is our Fourier law of heat conduction, where heat flux is minus k times gradient of T. Okay, so this minus sign is because uh, the heat flux flows from higher temperature to a lower temperature. So if you take a temperature gradient, it will be negative, but heat flux is flowing in that direction. So in order to correct that, we add a minus. Okay, so that's what this minus is about. This is what Fourier law of heat conduction. and we introduced a parameter called thermal conductivity. So this thermal conductivity has a unit watt per meter Kelvin or watt per meter degree Celsius, and this thermal conductivity is responsible for transferring the heat. We call it transport property. So this is one of the transport property. Now, uh, uh, so different materials, transports heats in a different way, and will correspond to this thermal conductivity K. For liquids and gases, it's going to be molecule colliding with each other. So molecular collision is responsible for thermal conductivity. But for in solid, molecules does not freely move in solid, right? So uh, only the uh, electrons can move around, or the holes can move around within a solid, or it can also be due to a lattice vibration because of vibration of the your lattice in solid, in any unit cell, that is responsible for thermal conductivity. So for non-metallic and crystalline solids which does not have free electrons, then they conduct heat based on lattice vibrational mode, and metals, they conduct thermal conductivity based on free electrons, okay, because of flow of free electrons. So which means it is also a good electrical conductivity, it also has good electrical conductivity, okay. And then we started deriving conduction equation. In conduction equation we know, so everything starts from energy conservation. um, Energy conservation you must have either studied in thermodynamics or even uh, in fluid mechanics. So energy conservation, from there we try to derive the heat conduction equation. So it is nothing but the, if you consider any control volume or any system, the energy entering minus energy leaving plus whatever the generated energy within the control volume is responsible for increase in energy within the uh, within that control volume. So that's what E in minus E out plus energy generated is nothing but the change in energy of that system. Okay, and so so the some heat is coming. You can assume that there is some Q double prime X heat flux is coming, and it is leaving Q double prime X plus delta X, and you can perform this energy conservation for this kind of system, and then you will end up having, so this is just X direction. Similarly you will also have Y direction heat flux, and similarly Z directional heat flux. So you can consider all them, and then you can write E dot in and E dot out like this, and you can add those terms, and then heat rate of energy generation, that could be either due to uh, you know nuclear heat generation, or electrical power. If you are sending an electrical power, because of resistance heat is getting generated, right? So all these things could be reason for rate of heat generation, and that will be nothing but the change in energy of that system, rate of change of energy uh, of that control volume. So that is what you write it like this. Here energy I is a uh, internal energy, okay. Now in the limit of this control volume tending to zero, so you will end up getting the equation for a point in your system. So that will look something like this, and we will apply, we don't know what is Fourier, what is this heat flux vector. So for that we use Fourier law of heat conduction. Fourier law of heat conduction says Q is directly proportional to minus of temperature gradient, and if you substitute them, you will end up having equation something like this. So in the left hand side you will have in terms of internal energy, but we want variable, or yeah, I mean the variable of interest is temperature, so we want the equation in terms of temperature. So we make few more assumptions. We will assume it's a simple compressible substance, and we will also assume that it's a pure substance. So when you make these two assumptions, so the this will reduce the dependence of internal energy to just two intensive property, which will be pressure and temperature here. It could be either pressure or temperature. It can also be pressure or specific volume. I think these are already you might have studied in thermodynamics. Pressure or volume, entropy or volume, entropy or pressure, entropy of temperature. So anything, but only two intensive properties. So any variable will depend on two other intensive properties. Okay. In here we are going to take pressure and temperature, and hence you can write enthalpy based on definition is internal energy plus P by rho, or I plus PV. Here V specific volume, 1 by specific volume is density. So uh, now you can write this in terms of internal energy, you can write in terms of enthalpy, and you can do this math, and then at the end, if you have to, if you assume it's a pure fluid flow, there is, I mean, there is no fluid flow, only pure conduction is happening, then this whole thing reduces to, you can express enthalpy in terms of this, and then this whole thing reduces to just rho Cp, and then there is beta T by dou rho by dou T term, right? Now you can substitute them here, and you will end up having this as your heat conduction equation. So you will have additionally this beta term. Beta is nothing but volume, uh, compressibility. Here you can, this part for solids is 0, so we can ignore this part for solids, uh, and the other terms, you can write this rho Cp on the on this side, but anyway, this is your final heat conduction equation. And so basically what this tells is this rho Cp is nothing but kind of like a Cp is specific heat capacity. So rho times Cp times this is rate of energy change, uh, or rate of energy stored or released by the system. That is going to be equal to the net heat flux gradient, which is due to conduction. So this part is conduction, this part is heat generation, and this is if you have any compressibility. But for solids, it's not going to be there, so this can be safely neglected to 0. So this will be your general conduction equation, and assuming that fluid flow is not present, or fluid flow is not going to take part in energy transfer. Okay, so that assumption is made here, so that's why it's called general conduction equation. Okay, not a general energy equation. So that assumption we will relax that assumption while we study convection. So while convection, there will be an additional uh, acceleration term on the left hand side of your energy equation. Okay, that's the difference. So you have equation like this. So if you want to solve this equation, find the temperature, you need some boundary conditions, and that boundary conditions, it could be either Dirichlet boundary condition, Neumann boundary condition, or mixed boundary condition. And anyway, so these are second order. Uh, Here it's partial differential equation, so you should have two boundary conditions uh, on and one initial condition, right? So for this, you need two boundary conditions and one initial condition in order to solve this at each direction. So this is a general conduction equation. Okay. So now we went on and we simplified it. 3D we do not want to solve. It's too complicated. So first we will solve a 1D conduction equation. In addition to that, we also made it's a steady, which means energy of a system is not increasing or decreasing. So the rate of change of energy, that term is going to be uh, is 0 basically. Okay, so if it's a steady state, the temperature is not dependent on time, so this part will be 0. And only 1D, so along x direction you will have a conduction and you will have a heat generation. Okay, and this will be your 1D steady conduction equation. Here k could be a function of temperature, we didn't make any such assumption, and heat generation also could be a function of x. Okay, now you can make another assumption that k equal to constant and qg equal to 0. Then this whole equation reduces to only simple d square t by dx square equal to 0. And once you have this, this is second derivative of temperature is 0, which means first derivative is constant, and If the first derivative is constant, temperature is going to be a simple linear line, and that is what you will see. Temperature is a function of a linear function of x. And similarly, you can also find heat flux vector, heat transfer rate. Heat transfer rate, you can write it as T1 minus T2 divided by L by Ka. So if you rewrite it like this, then your heat transfer could be uh, viewed as a current, and temperature difference could be viewed as a potential difference, and this L by Ka could be viewed as a resistance. So then you can actually draw equivalent electric circuit in order to easily solve it. So the electric circuit would look something like this. So the current is nothing but your heat transfer rate, and the resistance is because of the conduction, which is L by Ka. Since K is a thermal conductivity, resistance is going to be dependent on 1 by K times. So that's why you see L by Ka. Okay. And the heat transfer is going to happen only when there is a temperature difference. Similarly, current is going to happen only when there is a potential difference, right? But so that's what you see here. From T1 to T2 it goes. So here your conduction resistance is L by Ka. All right. Now, this is fine if you have a simple conduction between along the x direction. That is, if that is the only case, that is fine. In realities, you will have a wall, you will have a plain wall, and then on both sides you will have some convection happening, which is also going to take part in heat transfer. So at that time, you have something called Newton's law of cooling. So the heat transfer because of convection can be modeled using Newton's law of cooling. Similarly, we have Fourier law of heat conduction. For convection, we have Newton's law of cooling. So the Newton's law of cooling says Q is nothing but the heat transfer coefficient H. Okay, it's a heat transfer coefficient times area available for the convection times the temperature difference. Okay, so now let's say you consider a plain wall like this, and you have some temperature, some hot gases flowing on one side of the plane wall and cold gases flowing on the other side of the plane wall. Now you wanted to know how much heat is lost from hot gas side to cold gas side. Then you can say that you can find what is the heat transfer from hot gas to the wall, and you can apply, since it's in convection, you can apply Newton's law of cooling. And then across this heat wall you can apply Fourier law of heat conduction. And then again in the cold gas side, because convection is happening, you can apply Newton's law of cooling. So, and these three are going to be same. And since we don't know the temperatures at both the sides of the wall, we can actually construct a thermal circuit, and we no need to really find the temperature at the wall. Instead, if we know the hot gas and cold gas temperature, and if we know the resistance because of convection, we can directly find the total heat transfer rate, or vice versa. We can find the temperature. Okay, so you can construct a resistance in such a way that hot gas, initially it goes through a convection resistance. Convection also poses some resistance, which will be 1 by HA. So basically you just take this to the denominator, 1 by HA. Then it becomes I is equal to V by R, right? I equal to V by R, where V is the T2 minus T1, I is Q, and R is nothing but whatever is in the denominator is your R. Okay, for convection it is 1 by HA. For conduction is L by Ka, we already saw. And for the other side, cold gas convection, is 1 by HCA. Okay, now since these are like resistance in series, you can add them together and you will end up having TH minus TC by this whole thing. Okay, now this is for simple heat transfer when there is no heat generation. What if there is an heat generation? Then uh, also note that this conduction equation can be applied uh, within the this material, the plane wall. You cannot apply conduction on the outside of the plane wall in where the convection is happening, because it's clearly convection is happening, right? So you cannot apply the conduction equation there. So only the pure conduction, wherever the pure conduction happens, only then this equation you can apply, because it's a general conduction equation. So when there is a heat generation, you will have additionally Q G, and similarly you can solve this you can apply some boundary conditions. So here here uh, the problem is something like you have a plain wall, and you have some temperatures on both sides, okay, which is fixed. Now you wanted to know how the temperature varies within the wall, and the wall is also generating some heat. So if that is the case, how it is going to vary? And if you solve this equation, you will end up having this parabolic profile. You apply boundary conditions and you will end up having the final equation, temperature field uh, within this, and this is going to be parabolic. So you have this x squared term. So it's going to increase because heat is generated inside. Internally, the temperature is going to be more than the boundaries. Okay, so that's what you have here. And uh, so you can also find the maximum temperature you can find by taking this temperature field, or dt by dx wherever it is 0, that is going to be your maximum temperature. So you can take a derivative of this equation, and you equate it to 0 to find the x. Once you find the x, you substitute that x in this equation, you will end up having T max, and that is going to be something like this. Okay, and we all know it's going to happen at the center of this wall, because generation is happening on both sides. You have same temperature. If you have different temperature, then you might have a different peak at different places. Okay. um, Now these are all for uniform cross section. um, if you have a variable cross section, then your equation is modified a bit, like this: d by dx of ka dt by dx plus qg times a equal to 0. Okay, now here the area is also varying with respect to x. So if you take that into account, if you perform the numeric calculus, you will end up having qx to be something like this. Okay, um, this is just to show you how we can do it. Anyway, now this is till now we studied plane wall. Now if the conduction happens in a cylindrical geometry, let's say in a wire or in a tube, how the conduction is going to happen, then how the equation is going to modify. So the equation will also be modified into in cylindrical coordinates. Till now we studied Cartesian coordinates. So actually you can apply Cartesian coordinates equation here also, there is no problem in it, but your analysis will become too difficult. So you will apply everything in terms of x and y, but here it is circular, right? So you have the profile itself has an equation of circle in it. So solving it using in a Cartesian coordinate system is going to be very difficult, or it's impossible. So that's why we transfer our equation into a different coordinate system where you can easily uh, view the heat transfer in a different way, and we can apply boundary conditions so that you can end up having some analytical solution to it. That's why if it's a circular or cylindrical geometry, you change your coordinate system to cylindrical coordinate system. Now in the cylindrical coordinate system, the heat transfer could heat flux could propagate in the r direction, theta direction, and also in the z direction, right? So if it is in the r direction, you can take an infinitesimal strip and you can perform this uh, heat flux. You can perform basically the energy balance, and if you do that, you will end up having the energy equation to be something like this: d by dr of kr dt by dr plus qgr equal to 0. Okay, here again the Fourier law is going to be along the radial direction, which is kar times dt by dr. Okay, uh, this is like a 1D heat conduction equation. You can also generalize it, and this will be your cylindrical coordinate systems general heat conduction equation in all three directions. So you can perform this heat transfer uh, like we did for Cartesian coordinates. Like this you can try for cylindrical coordinates, and at the end you will end up having this big equation in cylindrical coordinate system. This is a general conduction equation in cylindrical coordinate system. You apply 1D you will end up having 1D assumption along the radial direction, you will end up having this equation. And uh, you know, without heat generation, your you simplify this relation and you apply the boundary condition, and you will end up having a relation for heat transfer along the radial direction. And also from heat transfer we can find the resistance, so that you can easily solve it based on electrical circuit equivalence. Okay, so that resistance for the cylindrical geometry would be something like natural log of R2 by R1, where R2 is outer radius by inner radius, divided by 2 pi L times K. Okay, L is the length of the cylindrical geometry. Now, um, let's say in a practical application, you wanted to add insulation to certain systems. Now, what should be the radius of that? How much material should I add on top of that insulation? So if you want to find that, then you apply this, so you will have some uh, heat trans heat transfer resistance to heat transfer across the insulation. You will also have some resistance to heat transfer at outside, because some convection is going to happen, that is also going to be there. So there's going to be two uh, resistance in parallel, so we'll end up having heat flux something like this. Now, only if your heat transfer uh, only if your conduction resistance is high and convection resistance is low. Basically, only if your resistance is very high, you will end up having good insulation, and that the maximum resistance for which you will get maximum heat flux is going to be your radius of critical radius. Okay, so which means when you do not have any insulation, your heat flux is going to be like this. And if you keep adding material, even though if it is an insulator, until a certain radius, the heat flux is going to increase only, it is not going to reduce, right? But the whole point of adding insulation is to reduce the heat transfer rate, right? Now, only if you cross this critical radius, you will end up having lower heat transfer rates. So that's what this analysis says, and this is the critical radius. And you always want your insulation to be uh, at least twice as more as the critical radius, because at critical radius you are going to have highest heat flux. So you want your insulation, the radius of insulation, to be more than this. Okay, that's the point of critical radius. You can do a similar for spherical geometry, and that's going to be, I guess, it's 2k by h. Okay, so it's a balance between conduction and the convection resistance. Now, similarly, you can do this analysis with heat generation, and if you do it, you will end up having your temperature profile something like this. And then we can also, as I said, we can do for spherical geometry. Um, you perform the same calculation. You can also write your heat conduction equation in spherical coordinates. Okay, now the heat transfer is going to be in r direction, theta direction, and phi, which is an azimuthal angle. So there will be r, there will be theta. This is in 2D plane. There's going to be one more along the uh, on the other direction, which is going to be phi. It's an azimuthal angle. So these are the two directions along which the heat transfer is going to happen. And you can write a full general heat conduction equation. Here we wrote it only if the heat conduction happens in the r direction. How does it going to vary is what we wrote here. Okay, this is for only radial heat transfer. And without heat generation, you will end up having temperature profile something like this. And with heat generation, you will end up having temperature profile something like this. Okay, so these are all uh, you know some formulas. You can either remember or you can derive it anytime, so it's not a big problem. um, and similarly, as I said, you can find the critical radius. It's the balance between conduction happening within the sphere and the convection happening outside this sphere. Okay, so your insulation should be more than this 2k by h, then only you will get lesser heat transfer. All right. And then we moved on to heat transfer from extended surface. So typically we want, if in the places where we want higher heat transfer rates, we added some additional surfaces to enhance the heat transfer capacity. So that is what we did here. If you have, let's say, a wall something like this, and if it is at some temperature, if you just allow heat transfer to happen, a convective heat transfer to happen, so it's going to just move along this, and it's going to take away some heat, and the available area is only this much area. Now, if the available area for convection is increased, then you can have more higher heat transfer. That's what we did. We added an additional extended surface. We call it fin. Okay, and along this fin, you are going to have convection, and that convection is going to take away more heat than it is supposed to take. Okay, so than the bare surface is supposed to take. So if you're planning to analyze such kind of systems, then um, again the same thing, the heat transfer is going to happen, but in addition the convective heat exchanges are happening, and we use Newton's law of cooling for that. So if you take an elemental volume, if you take something like an elemental volume like this, and if you assume heat transfer is particularly in this direction, then some heat flux is coming, some heat flux is leaving, and in addition some heat flux is also taking away some heat along the other sides of the fin. Okay, so so this is nothing but your perimeter. So that's what you see. So you have a convection term, and then you have primarily a conduction term, so which is going to be along this x direction. So this conduction term plus the convection term is the total heat balance, and that is how you got this equation. Okay, so this is your equation for one, if you are analyzing heat transfer in external surface in one direction. It is a 1D equation. Okay, and you can simplify it, you can give some new definition, new variable you can introduce, something like m is equal to square root of hp by ka, and you can non-dimensionalize it and you can solve it. Actually this is not non-dimensionalization, but it's just change of variable to easily solve the differential equation that we have here. Okay, now your temperature equation would look something like this, or the temperature profile would look something like this. You apply boundary condition. So but problem is, you will apply boundary condition here because we know the temperature here, base temperature. But what is the boundary condition here? That is in that there are like three kinds of boundary condition. One is, let's say your surface is very long, okay, such that at the end, we call it very long fin. At the end the temperature is going to be same as T infinity, whatever the fluid temperature. If that is the case, then your solution boils down to something like this, and your heat transfer rate would look something like this. Now but in reality it's not the case. You will have some finite length of the case. If you say it is some finite length, let's say this is the length, then you have to give some condition here. So at a length L, let's say the tip is insulated, or there is not very high heat transfer from that tip. That is, let's say if you assume that, then your equation would simplify something like this. So only difference between this and this is you have additionally this tan hyperbolic time in ml. Okay, that is the only thing. Now let's say I do not have insulated tip, but the area is sufficiently large, and the tip area, and the convection could also happen and could also cool down the temperature a good amount. Then what you have to do is you have to apply a heat transfer across that tip surface, uh, the energy balance across that tip surface, and that would give you a boundary condition which would look something like this. So initially we had a boundary condition which just says theta 0 at x equal to infinity, and then we say it's an insulated tip, so d phi by dx is 0. Now till now it was like a homogeneous boundary condition, but now we do not have a homogeneous boundary condition. We have the theta, the gradient of the theta depending on the theta at L. Okay, so that's the additional complication that we have here. So when you have something like this, then your temperature profile, if you solve it, you will end up temperature profile something like this, and your heat transfer would look something like this. So um, it's a it looks quite different from whatever we did in the previous case, right? So these are the heat transfer rates from the extended surface, but with different boundary conditions. Now, if you had some extended surface, we need to have some we need to quantify some performance, whether it is really useful to have fin or not, or if there is a fin, how effective is that fin. So if you want to know, then there are a few parameters. One is fin efficiency, the other is fin effectiveness. So the fin efficiency is rate of heat transfer from the base with fin divided by rate of heat transfer from the base if the entire fin is at TB. Okay, so uh, the basically numerator is the actual heat transfer that can happen from the fin, divided by denominator is if the entire fin is at base temperature. Okay, which means the conduction is very effective. There is very small conduction resistance. The conduction is very effective. Then temperature quickly neutralizes from the base to the inner uh, along the fin. So when you have such a system where T of x is simply equal to TB, then you will have some heat transfer, and that heat transfer is the maximum heat transfer that you could attain from attain from that fin. Okay, so efficiency you will have maximum at the denominator, so that's what it means. So Q actual, the rate of heat transfer from the fin, divided by the maximum heat transfer, which will happen only if the entire fin is at base temperature. So that's what this efficiency is. And you could quantify efficiency for different conditions, like for insulated tip. For long fin it is something like 1 by ml. For insulated fit it is, if tip, it's something like tan h ml by ml. Okay, for fin with convective heat transfer, you can you know convective heat loss, you can calculate from here. All right. Similarly, you can also find effectiveness. So the effectiveness tells whether it is beneficial, whether it's beneficial to add a fin. Okay, so which means, like, let's say Q with fins, what is the total heat transfer rate with fins divided by Q without fins. Okay, which means Q with fins will always be higher, so effectiveness will always be higher. Okay, um, without fins you will have only small cross sectional area across which the convection heat transfer is going to happen. That is what this is. It's base area times theta b, while if you have fin you have AF, which is the total area of the fin. um, so you can write this as effectiveness to be area of the fin divided by base area times the efficiency of the fin. Okay, this is also you can write it as. All right, so these are the two parameters. Now you can also have heat generation when you have fins, something when you have fins. If there is some heat generation happens in here, that could also affect your temperature profile and heat transfer rates, and that will look, so that your heat balance would look something like this now. So similarly, you take a elemental strip, you have some heat transfer coming in and going out, and then some convection is happening. In addition, some heat is also getting generated. That's what this QGAX is. Okay. All right. So then you can solve this equation for a similar. If you have some problem which involves this heat generation, then you can solve a similar solve this equation. But this is still 1D, but it is good. In at least you can get an idea how the profile would look. All right. And then till now we dealt in 1D. So we went on to study a little bit about 2D. Let's say if you have a 2D heat conduction equation. Let's say your problem is 2D. You have variations in 2 dimension. Then how will I get the temperature profile? How will I get the heat transfer along different directions is what we studied in this portion of the conduction, conductive and conduction heat transfer. So now your temperature field is not just a function of x, it's also a function of y. Okay, now we already derived this general heat conduction equation, um, and for the 2D problem, if you simplify it, your heat conduction would simplify to this. Given that Q generation is 0, it is a steady and it has constant properties. For example, K is constant. Okay, then you will end up having still rho Cp, we no need to assume it to be constant. Okay, it's because steady state will remove that part. We no need to worry. If you assume K to be constant, this dou square T by dou T square will be simply equal to 0. Okay, so this is what we call it as Laplace equation. It has a special term, Laplace equation. If you have any source terms, let's say Q generation is still there, then you will have this Q generation in this place. Then that equation we would like to call it as a Poisson equation. I think that is not covered in this course. It's just an additional information. So if you see a 0 here, it's a Laplace equation. If you see some source term here, it becomes a Poisson equation. Okay, now if you have equation something like this, it's an homogeneous partial differential equation. It is dependent on two variable, and if you have homogeneous boundary condition, and then you can apply something called method of separation of variables in order to solve this kind of equation, partial differential equation. So to get homogeneous boundary condition, we change the variables. We end up having this, and we have this homogeneous boundary condition, at least 3 homogeneous boundary condition and 1 non-homogeneous boundary condition. So this is required in order to apply a method of separation of variables. So as the name suggests, you have this dependent variable theta here, which is a temperature, and we are separating it as a two different functions or two different directions, f of x and g of y. So that is what, and this can be done only if you have a homogeneous equation and at least 3 homogeneous boundary condition. And when you do this, you can substitute them in this equation, and you will end up having this, and then you can rearrange this, all lot of math, and uh, you know solve them. You will end up reducing this partial differential equation in two dimension into two uh, ODEs, and if you have ODEs, you can solve them analytically. So that's what you have. This is the solution for that two ODEs, and um, uh, so you will end up having four constants, and these four constants, in order to find them, uh, you will apply boundary conditions, and one of the boundary conditions will lead you to a trivial solution, which we are not interested. So that's why um, we will seek for non-trivial solution. When we seek for non-trivial solution, we will end up having an eigenvalue problem, right? And that so that is nothing but lambda here. Lambda is n pi by a. Okay, so uh, you can get your solution something like this: summation of n cn, so sine of lambda n x and sine hyperbolic of lambda n y. Now the thing is, here cn's are constant, lambda n is nothing but n pi by a. So that is you select a lambda and you find c, you will end up having the solution for it. So to find cn, we apply the fourth boundary condition, and that fourth boundary condition will lead you to this kind of integral equation, and it will lead you to this kind of differential equation. You integrate it along 0 to a, because it's in terms of x, so you can integrate it along x, and then uh, you you will end up having this you will end up finding this orthogonality condition, and that will tell you that if m is equal to n, then only you will have non-trivial then it is not equal to 0. In other, if whenever m is not equal to n, then this is equal to 0. That's the orthogonality condition you will get, and uh, then you will end up having cn to be something like this. So first you select m and n. Okay, so n varies from summation of n, right? So n varies from 0 to infinity. You can vary. It's an arbitrary constant, and the solution is also kind of like a series solution. Um, so you choose a n, and only when m is equal to n you will find the solution. So you choose a n, then lambda n is n pi by a. Okay. You find lambda n, you substitute in this, you f of x, we know it's a boundary condition, you integrate it, you get the cn. Okay. Similarly, you do it for every n, and then you substitute it in this equation, you will end up having temperature profile. But in practically, you cannot go till infinity to find this temperature profile. So usually people do for, like, let's say 12 terms or 14 terms, sometimes 16, 20 terms also. Okay, to it will just improve the accuracy. So now we saw that it is for we just had like one f of x equal to 100. Now if I have two boundary conditions which are non-homogeneous or inhomogeneous, then you can actually do something called superposition. You can divide them into two different problem, and because your counting equation is linear, you can divide that, and which will lead to three homogeneous and one inhomogeneous boundary condition. Similarly goes with this, and then you will solve this equation separately, and then you add them, these two, you will end up having the solution. So that is how you solve it. Similarly, this is another thing. If you have a melting happening, your interface is going to move down. So at that time, how will you take care of the boundary condition is something called interfacial, stiff and interfacial boundary condition that we discuss. So in that case, your boundary condition will depend on the mass flow rate of evaporation or freezing. In this case, it's freezing. Okay. Anyway, so this still now it's a steady conduction equation. So we did 1D steady conduction equation, and then we did 2D steady state conduction equation. But unsteady also we may need to understand it for different applications. One of the application is this quenching problem. Let's say if you have something and you want to, some hot material, you want to quench it fast, quench it, then you should know what are the conditions I should be having in order to quench it at a certain rate. So the rate at which you quench a material is going to modify the microstructure of it. So that is one of the practical application that you will apply this unsteady heat conduction equation. So in unsteady heat conduction equation, we can either assume along x also it varies, but it just complicates the process. So we take something called lumped parameter approach. So along space it does not vary, but only with time it varies, which means it quickly neutralizes the whatever the temperature disturbance that is going to get throughout the body. So along x, y, and z, there's no change in the temperature. So that's why we call it zero dimensional problem. And you can also apply energy conservation as before, and there is no energy entering or leaving. It is at some temperature, only energy is leaving out, and so this is like a sphere, hot sphere, and cold environment. So the energy is going to continuously leave. So E dot will be there. E dot generation is not there because initially it's at high temperature, and the energy, it's going to continuously cool down. So you will also have uh, change in energy term. So it's an unsteady problem. So the energy will be leaving either by convection or it can also leave by radiation. So if, let's say, if convection is dominating over radiation, temperature is not that much, let's say 400, 500 Kelvin, then your lumped parameter approach will give you temperature profile something like this. And this actually gives you a new parameter called time constant, uh, which just says that what is the typical characteristic time that it takes for the temperature to cool down. Okay, so here probably it's like 67% of the temperature difference here, because since you have e power 1 is 1 by e power 1, I guess, is 0.67. So this is the time constant, and we introduced a parameter called Biot number. Biot number is going to say whether you can assume that temperature is not varying with respect to x. So that you can assume only if your thermal conductivity is very high such that it quickly neutralizes, or in other words your heat transfer coefficient is very low, so it's going to slowly lose energy to the surroundings. So that is the thing here. So Biot number is HL by Kc, and um, it's nothing but conduction resistance by convection resistance. If conduction resistance is more, then Biot number is more, then lumped parameter analysis is not valid. So you need to have Biot number to be very much less than 1. Only then lumped parameter approach could be valid. Okay, and you could actually expect some questions in this thing, Biot number, and solving the temperature profile, time it takes for the sphere to cool down. Similar kind of questions you can expect uh, in your exam. Okay, so that is one thing in quenching. The other is also in uh, you know in casting, in the riser design. You want your riser to solidify at a slower rate than the entire mold, okay, than the entire casting material. So you want this va by riser to be much greater than v by a of the casting material, okay, so that riser will not solidify before casting, and if while the casting material is solidifying, if it creates any pocket, the riser will provide the molten metal into it. So that is what this is, and we also introduced something called Fourier number, which is alpha t by LC square. LC is a characteristic uh, length scale here. The characteristic length scale is nothing but your area, uh, surface area by the uh, volume. Okay, volume of that object. So for sphere, it's going to be something like d by 6. Sometimes people do r6 by d. No, no, it's d by 6. Yeah. Sometimes people also take just d. So that is also people do it. It's a characteristic length scale, you can say. Okay. But in general, its definition is area, surface area by volume. Okay. All right. And then now till now we did lumped parameter analysis where our temperature is just a function of time, it's not a function of space. Now let's say if you have similar plane wall, initially it's at one temperature everywhere. Now uh, uh, now I mean the boundary condition is at t naught. Now how much time does it take to uh, this plane wall to reach that temperature? If you want to do that, then your problem becomes one dimensional in space, one and also unsteady, one dimensional in time. Okay, so your equation would look something like this. So initially it will be at ti, suddenly you expose it to t naught. Now it has to adjust to this t naught, and again for this you have some boundary conditions, uh, and you have some uh, governing equation, which is also again it's a uh, homogeneous governing equation, linear governing equation, and your boundary conditions are also looks like uh, you know uh, homogeneous. So you can perform again the same method of separation of variables, but now it is in one is in x, one is in uh, temperature, sorry, time t. Okay, one is in space, one is in time. So you'll be having a quite a little bit different. So there it was like both sine and sine lambda n and sine hyperbolic lambda n, right? Here there is one exponential term, exponential decay, since it's a negative exponential decay, and there is a cos lambda n term. To find Cn, again we find the orthogonality condition. You will apply the final boundary boundary condition, and you will end up having Cn to be something like this. You find Cn, you substitute in the equation, you will end up having temperature profile. So this is how the temperature profile would vary with respect to time. Okay. Now here the boundary conditions could also be convective boundary conditions, and if it is convective, then we have to modify our boundary condition, and when you modify it, you will end up having a different solution. So basically, the eigenvalue changes. Okay, you can repeat this operation again, lot of mathematics, and you will end up having Cn to be something like this. Your lambda n will be here. Okay, so before it was lambda n is what do you call 2n plus 1 pi by 2l, but now lambda n is obtained from this transcendental equation. Where is that equation? This equation. Okay, cot lambda nl equal to lambda n lambda ml by Biot number BIL. That's the difference between when you have a fixed boundary condition and when you have a convective heat transfer kind of boundary condition. Then we this is like an finite medium. Now let's say if you have an infinite medium on one direction, semi-infinite medium on one direction, then again governing equation is not going to change. It's just a change in time is there, and then there's a x dependence. Uh, but only thing is we need to analyze it a little bit differently. So we find the similarity parameter. Here again, it is also you can use method of separation of variables. So this is kind of like a separation of variable only. But only thing is this f of x is already known because it's a similarity parameter way. So f of x is just x, and you have g of t. Okay, and then if you use this as a similarity parameter and you can substitute in this equation, you will end up having uh, you will be end up finding this function, and so your similarity variable would be simply x by 2 square root of alpha t, and then perform a lot of mathematics, and then at the end you will end up having temperature profile to be an error function of eta, your similarity variable. So your temperature is going to just depend on similarity variable, where the similarity variable is a function of both x and t. Okay, okay, here the similarity variable is x by 2 into square root of alpha t. Okay, um, yeah, it could be either error function of eta, or you can also write it in a different way. If you write it in ti form, you will have to write it in error function complement of. All right, so this is what we did in the conduction. We started with deriving general Fourier law of heat conduction, and then general conduction equation in 3 dimension, and we simplified it for 1D steady state heat conduction equation. We also did it for heat generation, and then we went into moved on to cylindrical geometry. Um, Similarly, in 1D, in the radial direction, how the heat conduction equation simplifies, and we saw its solution, and with heat generation how it is going to vary, that is also we saw. And then a new concept called critical radius we introduced, and that critical radius will tell you what should be the heat transfer, how much should be your radius of insulation should be in order to have some insulation effect. Okay, so this we did for both cylindrical and spherical coordinate, and uh, for spherical coordinate again we did heat conduction analysis along the radial direction, and while doing so we also represented heat transfer with a equivalent electrical conduction, equivalent electrical circuit, and we can analyze it based on resistance. And then we moved on to heat transfer in extended surface. We introduced fins, and did energy balance for it, and there are three different kinds of boundary conditions that you can have for a fin. uh, a very long insulated tip, or convective heat loss tip. And we also defined two parameters: fin efficiency and fin effectiveness. So once this is done, we went to 2D problem. In 2D problem, we use method of separation of variables to solve a Laplace equation. And after 2D problem, we solve one unsteady equation. In unsteady equation, the main thing that you want to focus for at least your exams is the lumped parameter analysis. Um, but still, you could expect some word problems from the uh, you know the semi-infinite medium, and also the plane wall uh, plane wall uh, unsteady heat conduction, transient heat conduction on the plane wall. So you could expect some word kind of problems, because in the I don't think so they will be asking you to do these calculations in exams. Okay. All right. And after that, the next part, second part of this whole course is a convection. And uh, convection, we know it's nothing but the fluid is moving. Okay, the fluid is moving and the heat transfer is happening. So basically you can say it's like advection plus conduction. That is what we call it as convection. Advection means just the motion of the fluid. That's what advection means. So advection plus convection is what advection plus conduction is what convection is. So we initially started with Reynolds transfer theorem. Before that, we just quickly brainstormed what that convection is going to depend on, and that is going to depend on. We initially started with a lot of parameters, and we reduced it to just Reynolds number and the Prandtl number. Okay. Um, so initially, this is the Reynolds transfer theorem. It's like it's for any property that is getting transported. You can write the governing equation for any property that is getting transported. Here the any extensive property is n, and the intensive property, I think we are representing it as a theta eta. Okay. So you can write the Reynolds transport equation as something like this. And if you change this n, you will end up having conservation of mass, momentum and energy. And here the fluid is getting transported, and with the fluid energy is also getting transported. That's why we need to study this Reynolds transport theorem, and we need to develop conservation equations for you to study both mass and momentum and energy transfer. Okay. So for mass, you just change the property n, capital N to be m and small n to be 1. And sorry, small n is the intensive property, eta is, I think, the unit vector. Okay. Now for a system, by definition system means fixed mass, so you will have the change in mass of the system is 0. So if that is the case, you will have a conservation equation for mass. For non-deformable CV and for stationary CV, you make that assumption, you will end up having uh, relation something like this. Then you apply Gauss divergence theorem, convert the control surface integral to the control volume integral, and when you do it, you can write it as a integral of control volume. Then you can drop the integral, you can write the differential equation for continuity, or conservation of mass, which we call it as a continuity equation. Okay. And uh, we define something called rate of volumetric strain, which is how much strain as a volume it is going to uh, experience, and that is nothing but summation of this velocity gradient along heat direction. Okay. um, this If the rate of volumetric strain is 0, um, then it becomes an incompressible flow. Okay. um, so this whole part will be 0 for an incompressible flow. This is 0 for an incompressible flow. It's called kinetic kinematic parameter. It does not say anything about the mass conservation. Okay. So ideally, it's not like density equal to constant will lead to incompressible flow. Density equal to constant is a special case of this incompressible flow. Okay. So not necessarily density needs to be equal to constant for an incompressible flow. And um, one of the cases phase change that we discussed, and the second is the conservation of momentum. In again we do the same RTT for the conservation of momentum. In conservation of momentum, the change in uh, the external force that we add, it can be either two ways. One is surface force and other is body force. The surface force is because of the traction, uh, and we define something called traction vector, and then we entered that it is going to depend on stress tensor. The relation between this traction vector and the stress tensor is given by the uh, something called viscosity, which is a second order tensor which maps the sorry, you have the traction vector, and uh, you will you have the stress tensor, and it's a second order tensor. The stress tensor has both uh, the surface it is acting and also direction on which it is acting. Okay, so the direction of force, but that force acts on a surface, so that direction normal to that surface is this I, and the direction of force is J. Okay, so each surface can have three you know stress components. So we try to correlate this traction vector, and it comes out to be traction vector, uh, while if you are this is the traction vector in this side, so you can represent that in terms of stress tensor times the orientation vector. So when while you are mapping the traction vector on a certain orientation, you have to map it using a stress tensor. So that is what we wrote here. And on stress along x and y, this is the Cauchy's theorem. Okay, the traction vector along any arbitrarily oriented surface is it can be represented in terms of along stress tensor along x, y, and z. Okay, and that is what we derived here. A bit of mathematics, but at the end, this is the Cauchy's theorem. And when you apply angular momentum, what happens is this: you have this 9 components of stress tensor reduces to just 6 by telling that tau ij is tau ji, and hence you can write the traction vector in either of this form. So at the end of the day, we are interested in surface forces. So the surface force, it's control surface integral of traction vector times dA. Okay, now the traction vector can be replaced with stress tensor and the uh, normal vector, and you can body forces you can write, and then you apply Gauss divergence theorem for all the control surface, and you will end up having this Navier's equation or Stokes equation for this uh, for this fluid. Now we don't know what is this stress tensor. This stress tensor, we have to express it somehow. This you have additional 6 unknowns in your equation. So that's when you need to express this stress tensor in terms of all the other velocities, and that is given by the constitutive equations. Okay, so constitutive equation will relate the stress tensor with respect to other variables such as velocities and pressure. Okay, now this stress tensor can be either written as addition of hydrostatic and deviatoric, and the deviatoric is related to the velocity gradients for the Newtonian fluid, I guess. Yeah. um, Now this part is nothing but you can write it in terms of rate of deformation tensor, and so at the end of the day, for a Newtonian fluid, this stress the deviatory part of the stress tensor should be uh, linearly dependent on the rate of deformation tensor. Okay, and that you can map these two tensors by a fourth order tensor in between, and that fourth order tensor isCijkl. And now if you assume it's an homogeneous and isotropic fluid, now this since it's a fourth order tensor, you are going to have 81 unknowns. So from 6 we went to 81. So now that's why we want to do some assumption, reduce these unknowns. So we have this homogeneous and isotropic assumption. We reduce from 81 properties to just 3 properties, and then we apply the what do you call this angular momentum conservation here, and you will reduce this 3 also to just 2 by equating beta and gamma. So you will end up having simply the deviatoric tensor to be a function of alpha times rate of deformation tensor along in kk, and beta times this eij and eji. Okay, now this ekk is nothing but your dou uk by dou xk. So this is written in the Einstein notation. So you can write the deviatoric part as this, where One is volumetric dilatation coefficient, which is multiplied with the uh, continuity equation kind of term here, or it's a velocity gradient term. And the other part, you can write it in terms of, you can view it as the viscosity. Okay. And the hydrostatic is due to pressure, so that you can express it like this is a Kronecker delta. Now the total stress tensor, now it is expressed only with pressure and viscosity. Okay, pressure and velocity, with in addition to two new unknowns, which is a volumetric dilatation coefficient and viscosity. Now these two are properties of the material, so you know it, so it's no more an unknown. So your entire stress tensor is can be expressed in terms of other variable. So those six unknowns we have neglected. Only thing is we have additional unknown of pressure P. Okay. Now you have the uh, you have something called this pressure is mechanical pressure, this hydrostatic pressure we are talking, right? So you add the stress components, you divided by 3, you will end up having a mechanical pressure. And we are going to say that it's going to be same as thermodynamic pressure, and that is what Stokes hypothesis is. It is only true for a monotonic gases. And when you do that, you can reduce this lambda also. You can write it in terms of just mu, so you don't need this volumetric dilatation coefficient anymore. And uh, if you assume the flow is incompressible, then this lambda part term will go away, and hence, and the Stokes hypothesis, if you take into account and then you substitute them everything here, you will end up having something called the famous Navier-Stokes equation. So Navier equation plus the Stokes hypothesis plus the stress tensor expressed in terms of uh, I mean, you once you express stress tensor in terms of velocity and pressure, then you apply Stokes hypothesis, you will end up having Navier-Stokes equation. Okay, so there is no body couple, it's homogeneous isotropic and Newtonian fluid, and it's a Stokesian fluid. For this only this Navier-Stokes equation is valid. Okay, so now the unknowns are rho, P, U1, U2, U3. You have 5 unknowns, and heat transfer, if you add energy equation, you will have 6 unknowns. But continuity and momentum gave you only, so momentum is just 3 equation, continuity is 1 equation, so you have 4 equations. Energy equation you can add, you have 5 equation, but you have 6 unknowns, so you need to have one more equation, which is your equation of state, that is going to correlate your pressure, density and temperature. Okay, so once you have equation of state and your energy equation, your equations are coupled, and all these set of equations you need to solve for any convection problem. Okay, so we will go on and sorry, we will go on and we derived the energy equation. In the energy equation, the energy change of system is coming from first law of thermodynamics, which is Q and W. And W is again work done, it could be due to either surface forces or the body forces. Again, same traction vector comes in, traction vector then gets stress tensor comes in, and stress tensor you can express in terms of viscosity and other parameters. And finally you will end up having energy equation in this form. But here the energy is both internal energy and kinetic energy. So we want to express this in terms of just temperature. So first we change this total energy to internal energy, which is I, uh, by removing the kinetic energy part. To remove the kinetic energy part, we take the momentum equation, multiply with velocity, it gives you uh, kinetic energy equation. You subtract the kinetic energy equation with this total energy equation, you will end up having this internal energy equation. Now internal energy equation, you can convert the internal energy to enthalpy to temperature. Okay, and this stress term that we have here is, this is nothing but your viscous dissipation term. And we perform some analysis to reduce this, we to identify this viscous dissipation will always be positive, and it will contribute only to heating. Because of viscous, you will only have heating in your system. Okay, so this term can be expressed in terms of pdv work and your mu times phi, viscous dissipation. Viscous dissipation, this phi is viscous dissipation function, mu times phi is the viscous dissipative heating term. Okay, now As I said, you change the internal energy to enthalpy, and enthalpy you express in T and P, and then simple compressible substance, pure substance, no phase change happening. All these assumptions you take into account, and apply Maxwell's equation. In the end, you will have energy equation in terms of temperature. Now, um you still have this heat flux vector here. This heat flux vector is still, just from the Fourier law. Because of conduction, this heat flux is coming. So that's what you add here. Then you will end up having the energy equation for, convection. This energy equation includes the fluid flow also. So in your heat conduction equation, you simply didn't have this term. That's all. Okay, so this part is responsible for advection of your energy. This part, if you leave it out, then it will resemble the convection equation. Sorry, conduction equation. Again, this part will not be there. This beta T we also saw. This is for, is almost 10 to 0. It's like equal to 0 for solid. Okay, so you had heat generation, you had thermal conduction, and there is no fluid flow, so you didn't have this term. You will have energy storage. Okay, this was your general conduction equation. Now this is the most general energy equation you can apply. Now we applied it for the boundary layer development in a flat plate. So we know from the fluid mechanics, when you have a flat plate, because of no slip boundary condition at the surface of the plate, when the uniform flow flows, it will form a boundary layer, right? So the entire flow feels the presence of wall within the boundary layer. And um, here, in a, since if the plate is now heated at certain temperature and the fluid is at different temperature, now the temperature is also going to diffuse along the column of fluid, along the fluid. So that's why you will see a development of thermal boundary layer also. So in addition to momentum boundary layer, you will also see a development of thermal boundary layer. Now how different is this thermal boundary layer with the um, hydrodynamic boundary layer is given by the Prandtl number. The Prandtl number is very less, then momentum boundary layer is very less than the thermal boundary layer. If the Prandtl number is very high, then momentum boundary layer is very high compared to the thermal boundary layer. So well, the Prandtl number is nothing but momentum diffusivity by the thermal diffusivity alpha. Now um, since it's a boundary layer, you can apply um, you can derive boundary layer equations for the flat plate. So for momentum we already derived. For temperature, for energy equation we are deriving it here. We are assuming steady flow, incompressible, no heat generation, no we assume that it's a negligible viscous dissipation, so that we are simplifying some of the terms uh, in this equation. So when you do that, you will end up having simply this: the steady part has went away. Now you can take again the constant properties, and then you will end up having alpha here. And then we know the the boundary layer theory, which says that hydrodynamic boundary layer thickness is very much less than the length of the plate. Similarly, you can also assume for thermal boundary layer, again the thermal boundary layer thickness is very much less than the length of the plate. So when you do that assumption, you can simplify this relation based on the order of magnitude analysis. You will end up having thermal boundary layer equation to be something like this. So this is your energy equation, simplified form of energy equation for thermal boundary layer development at the flat plate. So your entire equations to analyze the convection problem of this thing is, you will have a continuity equation. This is your momentum conservation equation along the x direction, which is where the predominantly the flow is moving. Along y direction, it has given that dou p by dou y is 0. Okay, so there is no pressure gradient along x direction for this case. Okay, now yeah, there is no pressure gradient for this case. Okay, now this is your equation, momentum equation, for which you will use it to find the momentum boundary layer. This is your energy equation in the thermal boundary layer. Okay, now you like we do in hydrodynamic boundary layer, you have this u bar and v bar, like we non-dimensionalize the thing, the equation. You will end up having non-dimensional equation, you apply boundary condition, you find the heat flux vector. So the heat flux now it is going to be whatever heat that the heat conduction at the surface will be so you can see that. So this is just um, so no, I think we forgot to discuss that. Is it going to come later? I think it's going to come later. So this Nusselt number is nothing but a non-dimensional temperature gradient, and in the fluid. Okay, so you here it is just finding the equivalence between heat flux and shear stress, and this is what we call it something like Stanton, yeah, Reynolds analogy. So Reynolds analogy says that uh, Reynolds analogy is for Prandtl number equal to 1. If Prandtl number is equal to 1, then the heat flux can be effectively correlated with the shear stress. And if we say, then hence the skin friction coefficient CF can be used to find the Nusselt number. So that is going to be, Nusselt number is going to be simply Reynolds number times skin friction coefficient by 2. Okay, so that is the Reynolds analogy. And uh, the Stanton number is nothing but your Nusselt number by Reynolds number times Prandtl number. So it just says the convective flux by axial advective flux. It equates the convective flux and the axial advective flux. So now we assume the Prandtl number to be 1 in order to get this thing, but we do not want this assumption. We want to relax this assumption. So if we say that Prandtl number is very much less than 1, very much greater than 1, that kind of analysis we can do. When you say Prandtl number is very much less than 1, the momentum boundary layer is inside the thermal boundary layer. So your thermal boundary layer equation has to be more, it will now be based on the thermal boundary layer thickness, and your your velocity profile in your thermal boundary layer is going to be more or less uniform, because your momentum boundary layer is very small. It is, momentum boundary layer is here, and the thermal boundary layer is here. So this is Prandtl number very much uh, very much less than 1, right? So your momentum boundary layer is here, thermal boundary layer is here, which means the velocity profile, the thermal boundary layer is C, is going to be almost uniform, and that's why you directly take that. And if you perform that assumption, you will end up having del by delta T, which goes as Prandtl number power half, and you will be end up having Nusselt number to be relation of Beckley number power half. Okay, now this Prandtl number very much less than 1 is basically for liquid uh, metals. So you have both Reynolds number and Prandtl number dependence has to be power 0.5. Okay, this is for Prandtl number very much less than 1. Now you could do the same thing for Prandtl number very much greater than 1. Only thing is, now your velocity profile should be coming from your momentum boundary layer. So here we didn't substitute momentum boundary layer velocity at all. Momentum boundary layer has some velocity profile, we didn't substitute that, but here we have to substitute because momentum boundary layer is much greater than the thermal boundary layer. So your entire thermal boundary layer is within the momentum boundary layer where the velocities are changing. So you have to, I mean, here we didn't do, when you do an integral method, we have to substitute. So here we took velocity, order to be u times delta t. So this velocity order is also coming from, momentum boundary layer analysis, and this eventually will lead you to Nusselt number as a dependence of Reynolds number power half and Prandtl number power 1 by 3. Okay, so this is the difference for Prandtl number very much less than 1. It's Reynolds number and Prandtl number both are power 0.5. Here Reynolds number is power 0.5, Prandtl number is power 1 by 3. Okay, that's the dependence here. Now this is, we just did order of magnitude analysis. to get exact relation of Nusselt number with respect to Reynolds number and Prandtl number, we have to do more, uh, uh, you know, more analysis. And here we are going to do an integral method, similarly like we did for momentum boundary layer. So the integral method is just, integrate the boundary layer equation within the boundary layer. That's all. So you integrate, this is the your boundary layer equation, you integrate it within the boundary layer, and then you simplify them. You will end up having relation something like, you also, integrate the continuity equation, substitute them here, do all the changes, include Leibniz rule. You will end up having this energy integral equation. So once you solve this energy integral equation, you will end up having temperature profile. If you know temperature profile, you can find heat transfer rate. You can also find the non-dimensional temperature gradient of that temperature profile at the wall is going to be your Nusselt number. Okay, you can get a Nusselt number correlation. That's the whole idea. Now, as we said, we have to non-dimensionalize it. You non-dimensionalize it, you will end up having the energy integral equation to be something like this. Okay. Now, again, we do it for two different cases. Prandtl number very much less than 1, where u is almost equal to u infinity throughout the entire boundary layer. So you take this assumption. Now you have to assume some, like we do in momentum boundary layer, we will assume some profile for temperature, and we'll see whether that matches the energy integral equation. If it matches, I mean, we are actually fitting this equation for this. And when we do it, what is the value that we are getting is what we are trying to find out. So based on just boundary condition, you can find the theta. Now you substitute this theta in your energy integral equation. You will end up having an expression for delta t by x to be like this. So you can find the uh, thermal boundary layer thickness. And then we can go on and find the Nusselt number correlation. And that is going to be something like 3 by root of 3 by 2 square root of 3 divided by 2 root 8 times Reynolds number power of and Prandtl number power of. So you can still see you have this dependence. Only thing is, order of magnitude couldn't find this number, but the integral method found this number. Okay, this is Nusselt number which varies with respect to x. Now similarly, we can do Prandtl number very much greater than 1, and when you do that, as I said, you have to take into account of momentum uh, velocity profile, the velocity profile from the momentum boundary layer analysis, and that would be look something like this. It's a function of momentum boundary layer thickness, and then you do the same analysis. You will end up having uh, delta t by x relation to be something like this, and your Nusselt number correlation should be something like this. Okay, it's 0.331 Reynolds number power of and Prandtl number power 1 by 3. Okay, so uh, with this you can find what is your Nusselt number. Once you find the Nusselt number, you can find convective heat transfer coefficient H. So in the all the conduction problems, we directly, in all the problems, conduction problems, they usually give the conduction heat transfer coefficient. But in this here, the entire objective is to find this conduction heat transfer coefficient, which is H. Sorry, convective heat transfer coefficient, which is H, and that is obtained from the Nusselt number correlation. Or it's a Nusselt number. This is a expression for Nusselt number. It's not a correlation yet. So for this analysis, this is the expression for Nusselt number. Now, similarly, this is like external flow. Now you can have an internal force convection. In the internal, it's the same thing. Only thing is the boundary layer will develop and merge. That's all. So when you have something like this, you will have we similarly did energy balance for this, and when we did energy balance, um we actually kind of derive this logarithmic mean temperature difference in the convection class itself. When you have such variation in temperature between wall and the mean temperature. Okay, so this happens only when you have a constant heat flux boundary condition. So there are two kinds of boundary condition in this. We can either have a constant wall temperature boundary condition, or you can have a constant heat flux boundary condition. Now, based on this boundary condition, your convective heat transfer coefficient is going to vary. Okay, and we define something called bulk mean temperature, and to kind of evaluate the properties in that bulk mean temperature, and this is just a heat transfer analysis at the wall, and that will give you the mean temperature expression to be something like integral of UTdA divided by integral of UdA. Now, um, uh, when the thermal boundary layer are merged, the thermal boundary layer thickness is going to be just the width of your uh, width of your this is a two parallel plate, right? So width of the with separation width between the parallel plate, that will be your thermal boundary layer, and you can say that it is thermally fully developed flow. Now, for the thermally fully developed flow, the Nusselt number is constant because H and K are constant. So at the end, the Nusselt number is going to depend on, that's what we derive this. The Nusselt number is going to depend on H delta T by K, that we know from the external flow itself. Now the delta T is the width of the channel. So once the flow is fully developed, the Nusselt number is constant. It is not going to vary because H is constant, K is constant, and capital H width is also constant. Now, thus for fully developed flow, theta is just a function of theta is no more a function of x. It is going to be just function of y. Okay. Now, for constant wall heat temperature, we found that the temperature gradient along x is nothing but theta times dTm by dx. So we define something like mean temperature, right? So based on that, we are trying to express the temperature gradient in terms of this mean temperature, so that it will simplify our problem. Mean temperature is just a function of x, and theta is a function of y. So this will be if you substitute in the energy equation, we will have only one dimension, so you can solve them and get a result. That's the point. So if a constant heat flux, this is how this is going to look like. And then as I said, we are going to do some energy balance, and we will derive an energy equation for this. So there is some flux coming in, going out, the mass flux, and some heat transfer is going to happen along the walls. And when we have, your equation will reduce to something like this. And if it's a uh, constant wall heat flux, then you will have uh, uh, your you will end up having dTm by dx to be constant. So mean temperature is going to be linear. Okay. And if it's a constant wall temperature, then you have to perform some analysis, and then you will end up having the heat flux to be something like this, and the temperature uh, gradient or temperature difference is going to be your logarithmic mean temperature difference. And then uh, here it's hydrodynamically and thermally fully developed flow through a parallel plate. If we have both these two, then for constant heat flux, we have this as our energy equation. And if we simplify it, do a lot of mathematics here. So um, when we do it, we also need to know the velocity profile, right? So your velocity profile along this parallel plate could be, from the Poiseuille's flow, we already know, you can take that. Or we can also assume it's a plug flow, there is not much of distance. Or let's say if you have a turbulent flow, if you by chance, if you come to know that this is the velocity profile, then you can substitute that velocity profile also in this equation, and you can derive the Nusselt number correlation for this. So this comes out to be the Nusselt number based on the hydraulic, sorry, here it's hydraulic diameter. Nusselt number based on hydraulic diameter is nothing but 140 by 70. Again, so here the Nusselt number is constant. It's a fully developed flow, right? So the Nusselt number will be constant. Similarly, you can do for constant wall temperature, but constant wall temperature poses some difficulty. You need to solve using numerical method, shooting method, and if we do that iteration process, you will end up having Nusselt number in terms of width is 7.54. Similarly, you can express this, probably it's like 4 times the 7.54 is the Nusselt number defined based on hydraulic diameter. Now this is for parallel plate. Similarly, you could do for a circular pipe. Now your equation changes to in cylindrical coordinate system. In the cylindrical coordinate system, you have constant wall temperature, again constant heat flux and constant wall temperature. For constant heat flux, your dou T by dou Z is going to be simply dTm by dZ. Okay, so that's what we did before, right? Similarly, you can express that here, and so you can see. Similarly, you can express that here, and from heat balance, we know this dTm by dz is nothing but the wall heat flux. You can express in terms of wall heat flux, so that you will remove this dependence, and you will just express the temperature in terms of R, non-dimensionalize it. You will end up having uh, energy equation something like this. Now it is going to depend on again velocity profile. Here again you can take it to be a plug flow, or you can take it to be Hagen-Poiseuille's flow. We, this is we discussed in fluid mechanics classes, right? You must have studied in fluid mechanics classes. So from Hagen-Poiseuille's flow, you substitute your velocity profile here, and you solve this differential equation. It's a second order differential equation in terms of theta. NUD is constant. Nusselt number d is constant, and from here, from the boundary conditions, you can actually find out. From the boundary condition, you cannot find out Nusselt number. You need to use the definition of Tm. From the definition of Tm, you can find out Nusselt number to be 48 by 11. Okay. Now, similarly, you can do for constant wall temperature. It involves numerical methods. You need to iteratively solve it. When you do it, you will end up the Nusselt number to be 3.66. Okay. Here, it is not a function of Reynolds number or Prandtl number. It's since we are working on fully developed flow, it's going to be a constant, and these are the values. Okay. Now, if it's a turbulent flow, there is this famous correlation, Dittus-Boelter correlation, which is a function of Reynolds number and Prandtl number. And yeah, for wall temperature being more than the mean temperature, this is like for heating, and this is for cooling. For heating, it's N is 0.4, cooling it's N is 0.3. Okay. Now, till now we neglected viscous dissipation. Now, let's say if we have viscous dissipation, okay, then what is that going to affect our results? So, for that, yeah, we took some flow called quiet flow, where it's a purely shear driven, no pressure gradient. So by moving the one of the plate, top plate or bottom plate with some velocity, you will have flow develop, and that profile would look something like this. Velocity profile would look something like this. Now the momentum equations, if you solve the momentum equation, you will end up having the velocity profile to be something like this: u to be u1 times y by h. It's a linear profile. And similarly, you can do energy equation, but with the viscous dissipation function. Since we know velocity here, viscous dissipation is just it depends on gradient of velocity, so you can substitute them here, and you will end up having some temperature, and that temperature is going to be in a parabolic form. So you will have a heat conduction part, and you will have a viscous dissipation part. Now this becomes more and more important when the gap width is very very small, and because the viscous dissipation is going to involve heating your fluid to a very high extent than the heat conduction. So and then we introduced a parameter called Eckert number, which just sees the magnitude of kinetic energy to the thermal energy to understand whether this whether this viscous dissipation is important in your flow or not. Now if you substitute that relation in here, you will have Eckert number times Prandtl number in your total heat flux vector. Now the heat flux vector could be positive, negative, or even zero, even though when you have a heat transfer across a wall, you could have a heat flux to be zero when your Eckert number times Prandtl number is 2. Okay, so these are some interesting facts that came out of viscous dissipation. And then till now we were forcing your fluid. Now you can have a natural convection. Natural convection, um, basically the fluid flow development is also going to depend on the temperature. Okay, if there is no temperature gradient, there is no fluid flow, and hence your momentum equation and energy equation gets coupled. We cannot solve it separately. Till now we use momentum equation solved by you know, solved in our fluid mechanics class. We used uh, you know, velocity profiles from that, and then we solved it. Here we will not be able to do it. We have to, we are, these two are coupled. Okay, so to reduce the complexity a little bit, we applied Boussinesq approximation, where we said density. So basically, the coupling come from the density. So density is a function of temperature. So if the temperature changes, density changes, and hence momentum equation also contains density term. So in addition, you also have a gravity term. So Boussinesq approximation says this density is only added in the, density changes are only felt in the gravity, not anywhere else. So when you do this approximation, your equation reduces it simplifies a little bit, and you can express your y momentum equation in this manner. You can apply non-dimensional analysis. So at the end, uh, you, if the new parameter called Grashof number we introduced when we did the non-dimensional analysis, and a Grashof number by Reynolds number square, which is Richardson number, and that could be used to find whether the natural convection is needed or forced convection, whether the problem is a natural convection or forced convection. So if it is very much greater than 1, it's a natural convection. Very much less than 1, it's a forced convection. If it is almost equal to 1, it's a mixed convection. Okay, and we went on and we tried to solve this. So we did some order of magnitude analysis. Um, when we did order of magnitude analysis similar to previous cases, we were able to express this uh, you know, Nusselt number in terms of Reynolds number and Prandtl number. But for, you know, again, two different cases, Prandtl number very much greater than 1, where the Nusselt number is, you know, function of Rayleigh number. Rayleigh number is Grashof number times Prandtl number. Okay, Nusselt number is just a function of Rayleigh number. Now if you have a Prandtl number very much less than 1, here Nusselt number is a function of both Rayleigh number and Prandtl number to the power 1 by 4. Here it's just Rayleigh number power 1 by 4. Here is both Rayleigh number and Prandtl number to the power 1 by 4. Okay. This is about natural convection. We can also do more detailed analysis. We can do some integral method. We can do a more detailed analysis on this. But if you know dependence, that should be good. All right, and then we you know, studied about condensation. Condensation is a special topic in the convective heat transfer uh, you know, subject. So during condensation, um, you know, you could there are two kinds of condensation. One is film wise and drop wise. When in a film wise condensation, you because of condensation there will be accumulation of fluid, and that fluid after a certain point it starts flowing down. Okay, so when it does that, you will have heat transfer happening, and that is what we are studying here. We did something called Nusselt solution. So you have a flat plate, you it's at low temperature, and it's a vapor is you know, let's say steam. It's at higher temperature, saturation temperature. Now since it sees a low temperature, it starts condensing, and once it's condensing, it forms a big film and it starts flowing down. When it flows down, you can also have some conduction happening here, condensation happening here, some convection, heat transfer going out. Okay, so um, again we did since it's kind of like a boundary layer development, we did boundary layer analysis. We applied fluid statics condition. um, we used momentum equation, and then we ended up developing a velocity profile. And we also you know, from there we used mass conservation equation, and the heat transfer is going to be the mass of condensation times hfg. And so from here, we derived an expression for delta. Delta means the thickness of the film, and that is going to be a function of these many parameters. And at the end, we are interested in heat transfer coefficient, condensation, you know, based heat transfer coefficient, which is hx, which is a function of rho L, rho Vg, HFG, the subcooled temperature difference, thermal conductivity, viscosity, and all these parameters. You can, for if you have a vertical plate of finite length, you can integrate this hx for a finite length, and you can find the convective heat transfer coefficient. So the average conductive heat transfer coefficient is 4 by 3 times the heat transfer coefficient at a length L. Similarly, you can do for inclined plate. Only thing is your gravity term changes. Okay, so there we stopped. It's a condensation. It's a complicated problem, and boiling is even more complicated. So that's why we didn't do any mathematical analysis on this. Only thing we noted is uh, for delta T of around 5, you will have, there is the two kinds of regimes. One is nucleate boiling, after there is a film boiling. Similarly, in nucleate boiling, the bubbles nucleate and then starts growing and goes out. In the film boiling, this bubble merges after some time. After a certain superheat, the film merges and forms a film on top of the solid surface, where this film contains only pure gases, and gases have low thermal conductivity, so its heat transfer drops. Okay, and it falls to a minimum value called Leidenfrost point, and from there it starts increasing further. Okay, so this maximum point is a critical heat flux. um, so that will mark the transition from nucleate boiling. Okay, and finally we came to heat exchangers. Heat exchangers, basically, we even looked at it in the yesterday's class also. So you have these are practical, for practical application. You can have either two kinds of heat exchangers. One is direct and indirect. Here we studied only indirect contact heat exchangers, where you have one fluid flowing in a tube and the other fluid is flowing on top of the other tube, and across the tube there will be a conduction happening. Heat is getting transferred across the tube. Then now you can have two kinds of configuration: parallel flow, counter flow, and uh, you can also have some condensation happening on these tubes, or boiling can be happening on this tube, and based on that your temperature is going to vary. So along the length of the fluid flow, the temperature profiles are varying, and depending upon your temperature profiles, you will find a different heat transfer rates. Okay, now to quantify it, we introduce overall heat transfer coefficient, which just instead of here having a convection, conduction, and another convection, we simplified it with one parameter, one bulk parameter at a macroscopic point of view. Let's say if something is happening like this, heat exchanger can be you know uh, you know designated with some one parameter, which is overall heat transfer coefficient, which you can find it based on hi, h naught, and the thermal conductivity of the tube. Based on this resistance network, you can construct this and you can find it. So and then due to operation, it could become dirty and it could have some uh, additional heat resistance, so conduction resistance. So that we measure it using a something called fouling factor. Um, so as I said, there's the temperature is going to continuously vary. So if you want to find the total heat transfer rate, um, we cannot take a mean temperature. We have to integrate this along the length to find out what would be the total heat transfer rate. So for a parallel flow heat exchanger, this is going to be like this. In a parallel flow heat exchanger, and you express this for an elemental strip and you integrate it, you will end up having it's a similar problem that we faced in the convection. The temperature profiles are varying. So here also we will end up having LMTD, the log mean temperature difference. So we need to use this log mean temperature difference in order to quantify our heat transfer. So uh, this is applicable, or this can be easily applied only if you know the temperatures at the inlet and the exit. If you don't know the temperatures at inlet and exit, it's going to be a little bit difficult to find out using this formula, or you may need to use an iterative method. That's when we introduce epsilon NTU method. Okay, so in LMTD method, usually people use it only for design problems, where you want to find the area of the heat exchanger for a given temperature differences, and also overall heat transfer coefficient. What should be the area of the heat exchanger. What is the surface area that I should have within my heat exchanger in order to effectively have the heat transfer that I'm expecting. In the epsilon NTU method, we do not know. This is to quantify the performance of the heat exchanger. For example, like what is the highest heat transfer rate that I get for a given heat exchanger, for a given area, for a given overall heat transfer coefficient. And these are my inlets and mass flow rate and temperature inlet. What is going to be my exit temperature? If I want to find out, we use a epsilon NTU method, where NTU is number of transfer units and epsilon is actual heat transfer by the maximum heat transfer. And you can, after some lot of algebra, you can express the epsilon in terms of NTU and specific heat ratio for both parallel flow and counter flow. You will end up having two different relations. So for a given fluid, we know we can find NTU readily, and you can also find heat transfer, heat capacity ratios. And once you know these two, you can find the effectiveness. If you know effectiveness, you can find the max actual heat transfer rate. If you know actual heat transfer rate, you can that's basically quantifying the performance, and you can find the temperature differences at the end. So for boiling and condensation, you just have to take the heat capacity of that fluid, whichever is condensing, to be infinite. Okay, and then you can apply the same relation. So when you do that, when you take heat capacity to be infinite, the C bar becomes 0. So both of this relation will reduce to simply epsilon to be 1 minus exponential of minus NTU. Okay, so you can use this simplified epsilon relation, and you will be able to find the effectiveness. From effectiveness, you can find the heat transfer rate. So to quantify performance, you use epsilon NTU method, and to for the design, uh, you know, problems, you will use LMTD method. So that is how you analyze an heat exchanger. So that is where we stopped our course, and I will share this in the same Google Drive folder for you guys. But I also expect that you guys must have taken some notes from this thing. So I hope this is really helpful. I hope my uh, discussion sessions were also helpful for you throughout the course, and I'm very glad that you guys were able to uh, learn something new from this course, and I was able to be part of it. Thank you very much, and thank you, Avinash, for staying. And if you have any doubts, please let me know. I will be able to clear your doubts.
Thank you for the session, sir.
Thank you, Avinash.
So some beginning of the part, something seems to be new, sir.
Okay, so probably you may need to refresh your mind.
Yes, sir. Yes, sir. I'll go through it, sir, again.
Yeah, so it happens because the last 4, 5 weeks, 6 weeks, we were just studying about convection.
Yes,
We
sir.
totally must have forgot what happened in conduction, right?
Yes, sir.
So that is why it would look something like this. But if you read a little bit, you will be able to understand. It's just some refreshments we need. That's it.
Sure, sir. I'll go through it. If any doubt is, sir, I'll
Yeah, yeah.
mail you,
Please
sir.
email. Yeah, yeah.
Okay, sir.
All right, all right. Thank you, Avinash, and thanks for
Thank you.
people who were going to view it in YouTube. And I also thank Professor Suman Chakraborty for giving me this opportunity. Um, all right, then we will. Yeah, you feel free to be in touch with me in email. I will be able to answer your questions. And for everyone, whoever wants to, whoever has a doubt, I'll be able to help you through email. Okay.
Okay, sir. Thank you, sir. Thank
All
you.
right. Bye bye, Avinash. Thank
Thank you.
you, everyone.